will wait several minutes. Oh, no, it's time to start. Okay, so what we discussed last time. In the previous 3 lectures, we discussed empirical geometric correspondence. In the second lecture, we discussed superspaces. In the third lecture, we discussed differential form on, I would say, algebraic spaces. And direction integration. Important topic here was understanding that differential forms maybe I already found a different form. Maybe consider this function on t shifted by 1 x, where x would be a superspace. I explained it in an abstract way. Let me try to explain it, re-explain it again in terms of coordinates. Imagine that superspace has coordinates. That could be even or odd. It means that we have a concept of parity. How can we coordinatize t of 1 to x? For each xi, we introduce coordinate psi such that then we can write down the ramp operator as psi I d over dxi. It's definitely odd differentiation. This is d squares to 0. So then it's very easy to say the function of x and psi goes into function of x and dx that we studied last time. Well, now we introduced a concept, Bayesian integration. Of the superspace. And so on. It's better to write it deep side. Because it's not a differential form. And if I have some other monomial, it's a zero otherwise. It means that to determine Bayesian integration on a general superspace, we have to take odd coordinates. In particular, because if we change coordinate here, psi goes to lambda psi, the answer will change. special state. Here we have canonical. We have a form on X. Now, if I have this P of 1 to X, I have psi i's coordinates on P1 at some point next year on the final. And I kind of show that the following prescription. So here I'm taking the region, and here I'm taking convention over X. And here I have differential form. Written in terms of X and size. This is invariance. And leads to conventional, I don't call it conventional integral of omega of X dx. One can show that this is true for so this is true even for X being a superman. So there is a canonical integration of T1 of X. And here we have functions of X and psi. And now imagine and now I'm going to make a statement And statement is that if I integrate d, and this d is of course super d of g of x psi over t1 of x. And here I will write down the resonant. This thing vanishes. If even directions have no boundaries. And manifold is comfort. So for even directions, it's clear. Now let me show what's going on for odd directions. For odd directions, we have, here we have Berezin integral, and here we have d over dx that I'll call odd, and here we have psi even of something. But d over dx odd of something, when we take an integral, goes to 0. So altogether, we have the following formula. Now X is a superspace. And here we have df equals to 0. And of course I assume that even direction of x are local. Now, where I am going, explaining you all these details, I am going to the concept of the Rampus forward. Actually, what I'm going to explain you would be combination of three things. First thing would be the Rampus forward. Second thing would be odd Fourier transform. And third thing would be clever choice of the integral involving length function. So that's what I'm going to explain.
Excuse me. For x has some odd coordinate, then c has some even coordinate.
Yes.
And this Berezin integral is still defined like this, because here we see there are some d.
So Berezin integral is defined for odd coordinate.
So we need to change the measure to be something like capital dx, but small d per c.
Yes. So here we mean the Berezin integral. So what does it mean? It means that here we have even directions and odd directions. So for x odd, we have this dx. For psi even, we may write d psi. So that's what we are doing.
So if we first take the odd derivative, then it will contain just constant. So constant 1, then multiply this dx, it will cancel the Berezin integral.
So here is the property of Berezin integral of dx. The Berezin integral of d of something odd is 0. The run push forward could be explained in the following way. Let us take x equal to y times p. So how do we understand it? So this is some supermanifold along which we are going to take a push forward. And P would be understood as the space of parameters. So that's why I called it P, parameters. Similarly, we have T of 1 to x is T of 1 to y times T of 1 to p. Now, what we will do? We will take omega. That belongs to functions on T1 to x. Or you may call it exactly the same as to say differential formula. And we assume that it is totally closed on x. then we will do the following thing. We will take another omega, that is omega c. That will be also differential form on x. However, it would be kind of special. And this d omega c would be considered as delta form on cycle C that belongs to Y. Here I need to comment what do I mean. I need to explain a little bit about what deltas are. Delta of x, so how do we understand delta of x? Naively, for functions from R to R, delta of x is defined as follows. Integral of delta of x times function if phi at 0. How do we understand this formula? Since this is a function, it's better to understand this as one form. Now it's a singular one form. So people call it current. So it could be approximated by something like this. So here we have x. So that's what we actually have. Now, in the superworld, suppose we have odd manifold with coordinate theta, such that functions are alpha naught plus alpha 1 theta. What is delta? So, or how to solve such an equation. Some odd delta, and here we have phi, and we would like to get as a result alpha naught. So it's clear how to do it. Delta odd is nothing but, and it's interesting, it's nothing but theta. So it is a surprising property of delta function in the superworld. Now let us try to mimic the following thing. Integral of omega along the cycle C. How we can do it? We would like to find integral. So now let's for a moment take E being the point. And here we have some interesting differential form. So we would like to find this differential form. It turns out that it's possible to do it. For example, let E be a set of zeros of a function f. Now what we can write here? So this is an analog of delta function. However, it is clear that here degree of omega should be equal to dimension of C. And here so here we have the dimension of C. And here we have dimension of Y. And in this particular example, we need to see the degree C should be equal to 1. So we just write it in this way.
You mean f is an even function?
Yes, of course, f is even. So we are doing a particular example. This example could be generalized. Let's see with the set of 0 of the set of functions. I put alpha here. And here I have a product alpha from 1 to n. So this is the formula for the delta form on C. Now, this formula has a nice super space interpretation. And this is an even delta function. And this is an odd delta function. Because, once again, df alpha is psi I So this was situation where y was even. But you can easily generalize it to the case. Sorry. You can generalize it to the general case. So, idea in ordinary geometry imposing equation f equals to 0 corresponds to imposing equation f equals to 0 and df over dxi psi I equals to 0 in the superspace. Okay. Now finally I can come to the idea of the push form. I take omega multiply it by this omega c. Okay, it depends on epsilon, but I will later on I will tend epsilon to 0. And I integrate it over 1. I will get something. This would belong to differential form 1e. Now, several statements that I call it integral. D of integral is 0. Let us check it. D applied to integral dp. But since these guys, but here I can say that it is minus dy omega times omega cx. But then here I differentiate by parts, and I say that sorry dp. So here sorry, I don't need to do anything. But this is 0 because it's integral over y of dy. Sorry. That's how I should do it. So I should do it in 2 steps. Here I apply dp. Then I know that omega times omega 3 where dp plus dy closed. It was an original condition. So that's how I conclude that dp of this is minus and that's why this integral goes. And this is the Rampush formula.
Excuse me.
Yes?
In the general case, cycle is given by f equals to 0 and also the round differential action on f equals to 0. It's is it automatic? Because if you only define a cycle by f equals to 0 and do not impose this df equals to 0, it's like
So there are 2 things. First thing is so what is the cycle? Cycle is a line f of x equals to 0. There you go. In my case, f of y. what does this mean? What does this mean in the space of differential forms? It means that we are restricting not only y's, but also dy's. Not only y's are like this, but also let me say it again. F of y equals to 0. Okay? So y's are constrained. So what happens to differential forms? Naively, one may think, naively, one may think that differential forms that I will have would be differential forms on y chosen by ideal generated by f. But that's wrong. You actually have to add df. Example. Let y be c squared. Let us impose equation so with coordinates y1, y2. Let us impose condition y2 equals to 0. It would be c. So if we impose this condition on y, we will get c. So what are the functions of this c? What are differential forms of this c? Are polynomials of y1 and dy1. It means that dy2 goes away together with y2. That's why here we take a quotient not only by f, but this is an algebraic way, but also by df. In another way, it means that we have delta function in these coordinates and in their superpart. That's why delta function on C contains this term in even case times this term. This is a delta function on superpart. So I explained it in the case where it was an even cycle. Cycle given by putting to zero even function. But it always works like this. So, making the long story short, we have these integrals. And what else do we know about this integral? We know that if we change omega to d of some eta, the integral would not change. Why? I plug this d here and run the same argument. And here I just replace so it is dx of theta, and what I do then? I can say that this dx is with a minus sign. Ah. So this is 0. And here I see now, and here I have non-zero, I'm sorry. This dx could be decomposed into dy plus dp. dy goes away, and this is dp integral of y eta omega. So, when I change omega by d of something, then y, then I also depends by d of something. In this sense, we say that we have put forward of homology of x. So here I explain this integral. I kind of show that the change is d of, and this is the concept of push forward. And since I kind of explained everything algebraically, it goes to the super manifold case. It's just algebraic manipulation. Now we will make a 10-minute break, and then I will explain the Fourier transform. That's when we will continue.
点它 C， 然后我是 C， 如果这个 C 是有 odd variable 的话，它是长这样。就因为它这个说最简单的，比如说 C 就是有一个西塔的原因，
我觉得是。
那么它里面就会有一个就是 delta form 基本上就是个西塔，就没有那个第一这个东西。
我觉得是的，因为毕竟，很显然里面有 f square 有个西塔，
对，
它是 odd 方形的，
但它前面的意思就是，如果你只用西塔来代表这个 delta form 的话，那么这个第一西塔就不是零，就是你的这个 delta form 它现在这个东西它的得到 differential 是零。
对，但如果你 f 是 odd，那你前面有个 f square。
那 f 是 odd 这个定义肯定错了，对吧？这个定义肯定有问题。
我觉得
这样什么意思啊？
比如说 f 是 odd，它的 delta form 应该是就是西塔。
它 delta form 理论上来说，它前面写了一个证明就是西塔，对吧？
对。
但问题是，如果它 delta form 就是西塔的话，那你点让 difference act 往这个西塔的话，那就不是零，对吧？因为第一西塔就不是零，西塔就是一个正儿八经一个 base 上的那个，
比如说
variable 那种。第一西塔就是它正儿八经上的，它那个tangent 方向上的那个 variable，那个 coordinate。因为西塔本身是 base 上的一个 odd variable， 那 d 西塔就是它的那个 tangent space 上的正儿八经的一个 variable， 那 d 西塔就不是零。
对。
所以也就是说，如果你这么定义 delta form，可能它 dθ 就不是，
对，
那就不对了。所以它要强行加一个这个 dθ 等于0在里面，特别是，但就强行今天在这个里面再加一个dθ，就 dθ，但是它 delta form 就不是。In the previous example, if this cycle C is just defined by equation theta equals to 0.
Yes, and I realized that I forgot to explain to you this example. Let us come to this example. You see, algebraic approach allows you to construct a super version of cycles on the manifolds. I explained what's going on for ordinary cycles, but now let us consider a manifold with coordinates y, theta, sorry, not with coordinates y and theta. Here I put dy and theta, and this is the space of differential forms on C1. And now as Bowen proposed, what if we impose this equation? Theta equals to 0. So this is what element here that corresponds to such cycle. And the answer is yes. What we need to do? We need to write delta of theta. I'm writing it symbolically. Here is delta of d theta. So this is odd, and we can write it. So what is delta of d theta? It is e to the minus d theta. Remember that d theta is even. Squared divided by epsilon. Now, let us have a look what the Dirac operator is. D over d theta, and here we have d theta, plus, of course, dy, d over dy, but we don't care about. This is the object that we care about. Yes, this operator acts non-trivial. But this turns to 0 when epsilon is going to 0. So this is for smeared delta function, or it is theta delta of the theta. We act by the round operator, given the theta, it's this theta in front. However, then we have d theta multiplied by delta of d theta. It is still 0. And this is an example of odd cycle. We cannot draw it geometrically as a collection of points. But we can write it down algebraically. And what I was explaining to you in these lectures is that we can lift our geometrical understanding to algebraic understanding. In bosonic or in even case, sorry for physical terms, in even case, you can write what is going down here geometrically. Y cycle, there is differential form, you restrict it to cycle, everything is geometrical. But here everything is purely algebraic. And if you write everything purely algebraic, you can go to super case. So I kind of confirmed existence of such cycles. They could be of different dimensions because I can impose no equations or I can impose several equations. There are different. But that's why push forward depends on C that for me now is an algebraic version of a cycle. Now I would like to do Fourier transform. So it's not correct to call it odd Fourier transform, because it is odd Fourier transform only in the standard case. In super case, it will be ordinary Fourier transform, so it's better to call it super Fourier transform. So what do I mean by this? There is a space T1 of X, and there is a space T star 1 of X. And I can do Fourier transform in the fiber. So what does it mean in coordinates? I prefer to call dxi psi I. I take this thing. I'll explain it in coordinates. I have canonical pairing between element here and element here. And I will use it as a kernel of this Fourier transform. And what I'm going to do, I'm going to do Berezin integral with respect to psi. And I'll call it phi tilde that depends on xi's, theta x. So I go from functions here to functions here. So these objects are known as polyvectors. Let us see naively why they are polyvectors. Because we may expand them. Actually to infinity. And here we have and symmetry of coefficients here. Okay. It will not. Symmetry of coefficients depend on parity of theta. Would all x's I be even? That's the parity of psi. Parities of thetas would be 1. And these would form antisymmetric tensors. However, if parity of x and correspondingly parity of psi and correspondingly parity of thetas are different, it could be different. That's why people kind of missed these objects in 50s. In 50s, in mathematics, people studied only polyvectors where these thetas were all odd. But from the logic of what I'm explaining to you, it is natural to study all cases. Now it's very interesting to see what happens with the RAM operator. In local coordinates. We know Fourier transform. Multiplication by psi I goes into derivative with respect to theta. But here we have a super case. We need to check it. So what would be if I multiply here by psi I? It is clear that it's the same as to take derivative with respect to theta. So it works. And it works not only for even case, it works for the super case. And we are getting that D is going to what is called battalion-Minkowski operator. Now, what is good about having this battalion-Minkowski operator? We just did the Fourier transform. Interestingly, we have this second order operator. As a transformation itself, it would be useful if not the third step. And the third step is the following. Consider very special fluid. That's interesting. What kind of speciality would be in this fluid? I don't have an idea how people could guess it. You look with polyvectors times polynomials in algebra. I cannot explain how this could be guessed. It came only from trials and errors. And then the idea is to turn the Rampus form into to push forward of now. This push forward would be interesting if Boltine-Minkowski polyvectors are interesting. Otherwise, we are taking something, we are taking push forward. Why is it interesting? So what is so interesting about BV push forward? About BV polyvector? Let us compute. So we take two derivatives. And what we get is this. Mass so there is some sign factor that I don't remember, and the equation is to reconstruct signs. So closeness of BV push forward leads to so-called master or quantum master equation. Oh, I'm sorry. Yes. I multiply by h squared. Now, let us come to the idea that we had from the very beginning. Yes.
Previously, we learned the definition of the round push forward, and here this delta BV act on point vector BV is just like a round differential act on.
So this delta BV is the Fourier image of the round dimension.
So why do we call it push forward of point vector BV?
No. So it is an idea at the moment. So that's what I am going to explain right now.
So up to now, we just declared that this polyvector should be a closed form. Closed.
So idea is the following. We have the concept of the Rampus form. And here we can see. So at least it takes closed into closed. Now we do what is called Fourier transform. When we do Fourier transform, we take polyvectors on y times p. Now we do the following. Now we look at BV polyvectors here. And what is interesting is they go to BV polyvectors. Now here we have inside BV polyvectors, we have delta BV closed. BV polyvector. And they go to the delta BV closed BV polyvectors. So here polyvectors on y times p. And here are delta BV closed polyvectors on p. Now, it is interesting to know if condition for polyvectors to be if condition of BV polyvector to be delta BV closed is an interesting property. It could be an interesting property or it could be a non-interesting property. Okay? All this makes sense only if condition for BV polyvectors to be delta BV closed is interesting. If it's some stupid condition, we just don't care. And now we can write this condition. And now let us see if this condition is interesting. So this operation is called BV bracket, and you can read it out of this. Is it interesting or not interesting? So first of all, this is a theory in H bar. So if it is a theory in H bar, it is interesting to look at term H to degree 0. If we look at term H to degree 0, first term drops out, and we have this condition. Now it's interesting to see if this condition is interesting or not. Inspect simplest case. So simplest case is where S is a function. There is nothing to study because for functions do not depend on thetas, so everything is trivial. Inspect simplest case, where S is a vector field. So we compute the bracket of theta I, Vi of x, theta j, Vj of x. And this is already interesting, because this already gives condition that is the home side. Of vector field to be homological. So that squares to 0. So it's obvious assignment. Another example. And simple computation show that it is a pair of two conditions. A, vector field is homological. and condition gives f is invalid. So second condition could be easily made on the board. We differentiate by theta here and by x here. Okay. So it is an interesting situation. Interesting. And we know, in particular, that homological vector fields correspond to L infinity algebras, and in particular correspond to Lie algebras. Okay. But now I need to show how it works. I need to see what happens with the cycle C when I'm doing this Fourier transform. So I will make a statement. And statement is the following. So I'll keep this picture. Statement. But before I do the statement, I need to say the following. Space T star shifted by 1 x carries a natural symplectic form, a natural odd symplectic form. So of course you know that space T star without shift carries a natural symplectic form. So suppose here coordinates are x and coordinates here are t. I put subscript because these are coordinates in the cotangent one. So this natural symplectic form is nothing but this. You take a tangent vector to x, you take a tangent vector to cotangent, tangent vector to cotangent is a vector from cotangent, and you take a pairing. Now I am making a shift. So t's go to thetas. And I have this differential form. So this differential form is called PV symplectic form. So, from the course of classical mechanics, you know that there is a concept of Lagrangian submanifold. Lagrangian submanifold inside the symplectic space sim is such that omega restricted to L when in classical mechanics with standard symplectic form there are examples. And these examples are, I would like to write it here on this board. P I equal to 0. It's a very Lagrangian submanifold. Xi equals Xi naught. It is a Lagrangian submanifold. There are other Lagrangian submanifolds. And among them, I will mention so-called conormal bundle. Take a cycle C in X. Take such vectors T that the pairing of these vectors with tangent vectors to C equals to 0. So there is canonical pair. Now this is by definition a Lagrangian submanifold, but I constructed it using a cycle C in X. Okay. So why did I recall this classical mechanics story? I recalled it because I need to see what would happen to the process of integration over the cycle C, and I explained it already algebraically, if I do odd Fourier transform. Okay? So I have a function that defines the next instance. So they are super coordinates. And I multiply it by omega that depends on C, take the kernel and integrate. So the question is, could I understand it in terms of a field? And the answer is yes, I can. To do it, I need to do the inverse Fourier transform. I just want to plug it here. I think it's clear that this is the inverse Fourier transform, like an ordinary theory of Fourier transform. I need to distinguish thetas because there is theta standing here and there is theta standing here. So I call this theta tilde. So relative знак will be minus.
Excuse me.
Yes?
Do we still have an integration over some y? Because here it's not complete push forward.
Here we have.
I mean, here we only do Fourier transform, but we haven't do.
So we take this inverse Fourier transform and we plug it here.
Yeah, in the first line, there is no integration over some fiber y. We only multiply this form f with delta form omega c, but there is no integration over y.
You are right. You are right. But that's what we want to understand. And we keep P as a parameter. You are absolutely right. And here we need to take the region over T shifted by 1. Let me call it Dy. And here we have this region. However, in inverse Fourier transform, I have integration only for theta. Thank you for reminding me this. Okay, here I am. And even put y and p are parameters, we are keeping it as fixed. So it's a formula. And what we would like to do we would like to understand this kernel. Depending on the cycle C. So let us do it case by case. So the simplest case would be the yellow case. Because in the yellow case, we say that here's an example. And here I have delta of psi, that is psi. So what does it mean? It means, in this yellow case, that I took alt psi equal to 0, all y equal to y0. In this case, the integral simplifies into integral over d theta tilde. All psi's are 0. Okay, it depends on sigma. And here I have f of y naught. Theta tilde. So what is this space? Okay, now x would be y. It would be the yellow space. Because y0 is fixed, however, I integrate over all thetas. Now let us consider the opposite case. Opposite case is red case. In the red case, omega c of y psi is just a constant. It's also a cycle. This cycle means the full space. Integral still simplifies because now it is 1. So, integral over y is a red integral. Now we need to understand integral over psi and theta tilde. Integral over psi now brings theta minus theta tilde. Now, integral over theta tilde means that I am replacing here theta tilde by theta. And this is the red integral. Again, it's an integral along. So red case, is an integral over y, keeping theta fixed. And now, what is interesting is an intermediate case. So again, it's an integral over Lagrangian submanifold. In two particular cases. Now, what is left is to show that in general case, we will have the integral over Lagrangian submanifold. So how to do it? We need to put something very explicit in terms of this omega c YF, but we know it. And here I will write moded over alpha. So now home exercise, home assignment. Show that this integral corresponds to the green integral. at least for alpha equals to 1. So idea how to do it. Take points on the cycle. Of course we have points on the cycle. And see, because we have delta functions of f. And then inspect what happens with the theta tilde psi integral. Okay. So the outcome of this is now this is a more general statement. So I showed the particular statement. Is that here we are taking integrals over Lagrangian submanifold in T star shifted by 1 to 1. So this is BV language. I gave you all inputs of BV language. When H bar is 0, we call classical mass translation. And you see that the only way to express this classical master equation and this BV push forward is in the language of the supermanifold. Now, what would we get in future? We will go from this BV language to topological theory. So our goal would be to explain what would be topological theories, what are topological theories, and how to construct all topological theories in terms of this BV push forward. This BV push forward would turn into a would-be functional integral in topological theory. So here I'm drastically changing the topic. So some kind of mathematical prerequisites were given. Let me give an announcement. It is good to have an announcement. All topological theories have the form, almost most, I would say most. There is an example. There is the exemption. Most of topological theories is the theories are integrals, BV integrals. Over a Lagrangian submanifold inside the space of maps T shifted by 1 sigma to T shifted by 1 plus d sigma y. So now we study this space a little bit. We study this space a little bit. In order to construct such a theory, you need to have a solution of a version of classical master equation on Y. So here I say version, however, if deep sigma is even, it's not a version, but exactly solution to classical master equation. And there will be many examples. So that's what I explained today. And I'll go to topological theories on my next lecture. So any questions?
Yes.
Yes.
Can you repeat how can you when you're given such Lagrange submanifold by these equations, how can you write out this delta form very fast?
Very fast?
Yeah, it seems to be very simple. You can
Okay, so that's what, okay, so that's what we discussed.
yeah.
So suppose we have t shifted by 1 to 1. Okay? Suppose I'm looking for special closed differential forms called cycles. So I thought the cycle is a set of points, but now it's not a set of points. Now it corresponds to equation f equals to 0. But I cannot put f equal to 0. I need to put f equals to 0 together with df equals to 0. So cycle is these two conditions together. So what I put? Delta f, delta df. So this is a cycle corresponding to f equals to 0. Why it is a cycle? Because I apply it here, and it doesn't matter what I have. This is 0. And this is true for both even functions or odd functions. Parity doesn't matter. This computation is purely algebraic. And then I plug the cycle here you may consider it as a part of a whole assignment. That we consider one part. No products. So this is algebraically a cycle. So if it is algebraically a cycle, I can study integral. And here I'm taking integral over psi. So without this term, it would be theta equals to theta tilde, and it will be correspond to cycle that is 1. 1 is also a cycle. It means the full space. But here, I just want to say that there are restrictions on thetas. So how do I get these restrictions? I am getting these restrictions by taking this psi integral. So I can say the following. Let me call this theta minus theta tilde theta minus. And I integrate over theta minus. I have a restriction on theta minus. So how does this restriction comes from? Okay, let me see. So I wanted to say that I am not integrating over okay. I need to think. Theta minus appears here. It also appears here. 1 second. I cannot ignore theta minus that stands here. Okay, I have some problem to do it algebraic. I know the answer, but how to explain it? But I have some problems to explain it algebraic. One second. Of course, the answer would be to integrate over psi. So, for those psi, I say it in an informal way, that are parallel to df, this integral goes away. For those psi that are perpendicular to df, I have to take this integral. Okay, so I got confused a little bit. Okay, think about this. So, would f be one of my coordinates psi nu? In this case, I will get here psi nu, and then I will get here the minus psi I, and here I will get psi nu. In this particular case, because of integral over d psi, I would omit one of thetas from the integral.
Excuse me, in this case, you assume f is just one x mu, right?
Yes.
The first term, delta f becomes psi mu.
Here I have delta x mu, but this corresponds to botonic piece.
The second part is delta. Also, there should be a delta. Delta df. So it's delta psi df.
No, so there is this object, and here is psi mu. And you see, this is botonic object. I don't care about. Okay, I care only about psi integral. I care only about psi integral, and in the psi integral, I have this. And now I am looking for the region where I integrate psi minus. And this region is the following. Without this psi, this region would be a point. Because integral over psi's would put me all psi minus without that. However, with this psi mu, with this psi mu, I would still have an integral over d theta minus mu. So it would be one-dimensional integral. So cycle would be in codimension 1, but I will still have one-dimensional integral over theta minus. So I would say that if you compute this integral, you would say that theta I should be df, so f has indices alpha. Theta I minus. And you will have to integrate over this rho alpha. So if you inspect this integral, so totally you will have the integral over product over alpha, d over alpha, delta of f alpha, product over alpha. So I would expect that the answer would be like this. So what would be this rho alpha? These rho alphas would be coordinates on this space. Here we have C, here we have C star 1, and these all rho alphas would be coordinates here. So this would be an answer. However, I cannot derive it immediately from the word. So for each function, you will have this theta minus. So this would be the answer. So where do they put the index? Yes, so. Okay, so home assignment would be to derive this formula. So so here is the formula. You should start from here and derive here. Okay, so next time we would go to topological theories. See you next Thursday.